All right, do you see me on screen with example 0.4? Okay, let's continue. Do you see me? Do you see screen? Okay, nice. All right, so we are dealing with example 0.4. Assume that the expected losses for a company last year were 40 million, in fact, observed 47. So the losses become larger. And we are dealing with the partial information. It was based on 12,000 observed claims, and in fact, a fully credible estimate of the company annual total losses were 18.5. So we are going to use this square root rule in order for estimate the total claims for next year. So typical situation for the company. We were expecting that the losses will be 40, but they are actually larger. So how can we understand what will be the losses for the next year? And we have only limited information to decide. So let's use example 0.4. The number of examples are messy, don't bother. These are just to let me know what kind of examples to place to the final exam amount. Okay, example 0.4. So we have the observed claims. They are 12,000. We have the required claims. They are 18,500. Okay, and we have 40 and 47 of the total losses. These are 40 and let's say observed was these are 47. Okay, so we have all the information to place inside this kind of formula, ZS1 minus Z mu. Okay, so let me place the formula here. The square root of observed claims over required claims plus times what? Times what we observed times observed losses plus 1 minus this thing. This is Z. Okay, let me place Z equals to that. Okay. Okay, so now Z 1 minus Z times the rest is the total loss. Okay, so far we have calculated, and let me use. So we have 45.63. So if we were expecting 40 million of losses and we got 47, so next year we'll rise the expectation and we will be expecting 45.638 million of these total losses. So actually really a useful formula to implement for partial credibility. Quite easy, I would say. So next thing, if you don't have any questions, if you have, please ask. Bayesian credibility. Let's move on to Bayesian credibility. This is different kind of approach. If theta is an unknown characteristic or parameter related to a population or random variable, then the frequentist statistic, frequentist statistician will attempt to make inferences about theta on the basis of the sample information X. So the Bayesian statistician, however, would always believe that there is additional prior information available about theta, which should be combined with the sample information X in order to make inferences about theta. So we are talking about Bayesian credibility here. In the Bayesian credibility, in the Bayesian approach to credibility theory, we would summarize collateral information about the unknown parameter theta, and by means of a prior distribution. As such, we really saying that the unknown parameter can be viewed as a random variable denoted by theta. The choice of a prior distribution for theta is often a subjective decision. Informative and accurate information is usually reflected in a prior distribution, which is centered near the unknown parameter and or is precise or has small variability. So given sample information X, we would determine the posterior distribution, and we use this to estimate the true value. Okay. So in the end, we should end up with this kind of z theta s plus 1 minus z mu 0. This is the classic example, is actually useful to estimate the expected aggregate claims when they are normally distributed. The classic example, I mean, the normal model of this Bayesian credibility. The thing which we ended with, I think, like lecture 13, week 13. The normal model, I have just placed the formulas, but we haven't dealt with the actual example. So the formulas are the same as in the lecture 13. And what actually we are dealing with is the estimate of theta. I think that the problem is here that theta small, here should be theta small. The other things are perfectly fine, okay. And credibility factor n or n plus sigma squared 0. It is both reasonable and clear from the last expression that in this model the credibility factor z is an increasing function. So I have placed all this information to the slide. What also should we know? Should we note that the posterior variance is actually the reciprocal of the reciprocals of sigma squared over n. Actually, this is this might be useful, but don't bother about that. Let's just move on to the example and just understand what's happening here with the numbers. Let's move on to example. Yeah, quite large. Okay, in past years, a log normal distribution has been used to model the claim size X in a portfolio of household contents policies. If Y is log X, then we have this assumption that Y follows the normal distribution with mean value of 6.9 and the variance of 0.1 squared. Okay, now we have changed the procedure. Okay, that's the initial units, the bias estimate. So actually, let's just place this information to R, and maybe this will be a little bit easier. So this is example 0.5. Okay. So what is actually happening here? We assume a normal prior for mu. Initial feelings of the new value of mu are that it will be approximately 6.4 and with 90% certainty in this interval. So 0.9, this is the 90% certainty, will be equal to the probability that 6.4 our mean minus 90% Q norm of 0.9 is 1.95. 0.95. No, we don't need Jacobian for now. This is not necessary. Actually, 1.64 here. So this actually minus Q norm of 0.95. So why I'm using 0.95? This is the question for you. So this is the information I am talking about, why I use 0.95. Anyone? Any ideas? The key is 90% certainty. So why with 90% certainty I am using 0.95? This Q norm 0.95 is actually the yeah. Yes. So we are dealing with two-sided interval, two-sided test for our normal distribution. And so if we are dealing with two-sided, then we need to divide by 2. So if we were talking about one-sided test, then 0.9, and we will actually fit with the 0.9. So for now, yes, that's correct. We're dealing this Q norm of the quantile of normal distribution with 5% on both of these sides. Okay, 6.4 minus the value, and this is actually less than or equal to mu, and greater than or equal to what? So the same value will be here. The only difference is with the sign. Okay, and let me put it inside the formula. So this is the quantile of normal distribution, and let's replace it with the number. What's the number? What actually I miss here? Who can find out what I am missing in this formula? There should be some parameter over here. So if you got this idea, you're great. So the parameter which I'm missing here is sigma 0. Because the value 1.64 is just the quantile of normal distribution, and to find out the interval, which is given 635, 645, we are dealing with the mu, the estimate, minus or plus quantile times value. So this is the actual correct formula, and we should also be less than or equal to here. Yeah, okay. So it follows that our sigma 0, let me open sigma 0, this is the value of 0.05 over our Q norm of 0.95. This is the value. So sigma 0 is actually 0.03. The prior distribution for mu is normal with the 6.4 as the mu, and the sigma 0 will be 0.03 squared. Okay, the posterior will also be normal with mean given by our formula over here. So we have just find out what sigma 0 squared is. This is 0.03. We also know, what else do we know? We also know the value of n. We should know it somewhere in a random sample of 40. Yes, so 40 is n. Then what else? Mu 0 is given 6.4, our estimate. What will be x bar? I think this should be 6.51. Okay, let's place everything inside the formula, and it should be completed. Okay, so where is my mouse? Okay, sigma 0. First of all, I'll place the whole formula inside, divided by, then here is sigma. Too much. Let's place it as S1, S0. So S0 is sigma 0. S0 divided by S0 squared plus S squared over n. So S squared is 0.1. S is 0.1. Okay, so this is the first part of the formula times y bar. Y equals 0. Hold on, not 0 6.51. 6.51 times y plus the second part of the formula here, s squared over n, the whole thing divided S0 squared plus S squared over n times mu 0. Mu 0 is 6.4 given, n is 40. Okay, so we have 169. Is correct or not? I think it's not correct. S over S0 squared. Yeah, S0 squared is the information over here. So we have to replace S0 squared, then divided by that times that 0 squared over n 0 squared plus x. Yeah, so now it should be 6.48, and this is correct. So to obtain a posterior with standard deviation less than or equal to that value, in this situation we need a sample of size n such that such as what actually we have just estimated 6.48, and this is the posterior, right? And the mean of this posterior is given by 6.48. So this is the mean of the posterior. This one. Posterior. And we need to estimate n. How can we estimate n? N can be estimated with this kind of value. Actually, this will be square root Okay, let's try. This will be 1 over s squared over n. Then plus 1 over s0 squared. Okay. Then this whole thing should be to the power of minus 0.5. So n is that n, and this should be less than or equal to 0.01. Okay, so we have to replace this n with maybe this is 0.03, n equals to 50, equals to 60, 70, almost, let's say 90. Yeah, 90, I think 89. 89 is larger, so n equals 90 is the thing that which we are looking at. So this thing should be less than or equal to 0.09. This is 0.1 by our task, and this is okay when n is larger than 90. Then is more or equal to 90. Yeah, I just used the how to say it. I just picked the numbers randomly and was quite lucky to find out the value which is okay. So 89 is not enough, but 90 is enough. But actually, you will have to replace everything to find out what n equals to and express this value. Or in another case, you might copy this formula to Excel and use the goal seek to find out the exact value. Because here the optimization in quite hard to set. This is not how to say it? This is not that visually appropriate to find out the optimization in R, but it is possible to make in R also. All right. Any questions so far? So we were dealing with what would be the bias estimate if the absolute value loss function were used. So the bias estimate, we assume the normal prior for mu, and we set the prior distribution with mu equals to 6.4 and sigma squared 0.03. The posterior, we also find out that it will be 6.48, and we obtain the posterior with the standard deviation less than or equal to 0.01. In this situation, we have found it is n more than or equal to 90. So quite a hard example in comparison to the previous ones, but still it is possible to deal with this task just by placing this same kind of framework and using it step by step. Okay, so next we deal with the different kind of example. Okay, so where's the we are considering the total claims of $42,600 on a group of 20 general insurance claims using a normal model with mean, mu, and standard deviation, 600 for the conditional distribution. And what do we need to find out? Then the data estimate is. So we need to use the normal model. to use the normal model. So we have to adopt some kind of a normal model for a normal model as a prior for mu, and the prior estimate mu bar will be the prior mean, and we will find out this prior mean as different than 2130. Okay, so let's say that okay, I'll place it here. Zero 0.7. Very hard question. So we adopt the normal approximation with 2400 and 150 squared. Let's say that as a prior for mu. The prior estimate mu bar will be the prior estimate mu bar will be prior mean, and mu bar will be 2400. Here is 2400. Okay, and no, it doesn't. No, yeah, like that. And from the general results, what do we have? The posterior distribution of mu is normal, with mean. What kind of mean we have? Actually, the posterior distribution is normal with some kind of mean and some kind of variance. Okay, I think that something missing, some information is missing here. Okay, some 42 over 20s to 130. So why do we get this to 130? Why do we get this to 130? The stereo distribution should be different to get us the Bayesian estimate. Okay, so what is happening here? So mu bar should be equal to mu 0. Then if we have it 1 over n. So mu, okay, let's try to find out. Okay, mu estimate is what? This is the fraction of nx n bar x. Then here is the sigma squared. Then we have plus this fraction of mu 0 over sigma squared 0. Okay, and this is just the top of the formula. This is the numerator. So we place the fraction. This is the fraction, and another one. In the denominator, we will have another fraction, n over sigma squared, and here another fraction plus so here the plus 1 over sigma squared 0. So if we are using this kind of formula, and x bar over sigma squared plus mu 0 over sigma squared 0, n over sigma squared plus 1 over sigma squared 0. This is the Bayesian estimator of mu, and actually we should obtain the value of mu 2250. Then using this formula, mu will be 2250. And what else? The variance. The variance will be 100 squared. So the Bayesian estimate will be like 5 over 9 times 130 plus 4 over 9 times 2400. So the weight attached to Z is 5 over 9. This is just the 0.55. So this should be fine. I won't put this example to the final exam. Don't worry. This is quite unobvious to calculate. Yeah. Okay. So this is the Bayesian estimate of mu star. This thing. Okay. So we have this weight attached. And if we adopt some different normal distribution and we obtain not the 2400 and 150, and if we change that to 250 as the prior, we will have different value of mu, and we will have different values of Z. Okay, so this is quite hard. Don't pay attention for this example. Okay, so let's move on. Now we are dealing with Poisson gamma model. Okay, Poisson gamma model. The credibility, the Poisson model actually is frequently used to model claim incidents. Let's suppose that annual claim numbers on a portfolio of policies are modeled by a Poisson distribution with a single parameter lambda. You remember that this is the one parameter distribution. We have only lambda as a parameter, and the prior information about lambda may be summarized by a gamma distribution, G of alpha and beta. And we might view lambda as the realization of the random variable lambda, which follows the gamma alphabet. So after collecting the sample information about claim numbers, we will over n years, we will have these values of Z and beta. So beta is actually alpha over beta over alpha over beta squared. The value here, alpha over beta, is the expected value, and here is the variance. So actually this is not equal to, but it is with 3 equal signs. It's almost k, but still. So how can we use the Poisson gamma model in our setting, actually? Okay, let's suppose that we have some kind of Poisson gamma. Okay, this is the Poisson gamma setting. Let's say that we have the gamma distribution with these parameters, and it is used as a prior for annual claim size. Is a prior for annual claim lambda. Okay, this is it. And that the numbers of annual claims observed in a 5-year period, and let's say that we place these annual claims observed are that let me insert R. So these are the claims 2, 3, let's say 6, let's say 0, let's say 3. So we have a 5-year period. We have annual claims observed here, and so then the posterior distribution for lambda given x is gamma what? Gamma 14 plus 3, 5 plus 1, I would say. So this is the x. C 2.8, and the variance of x is 4.7. Let's say that the posterior distribution is given what is it, 14 plus 3 and 5 plus 1. So it will be gamma 17 and 6. So this kind of this kind of distribution. So we have the credibility estimate. Credibility estimate is 17 over 6. This is 5, 6 times 14 over 5 plus 1 over 6 times 3 over 1. So is it okay? Target of assignment expense of non-language object. What does the non-language object? This thing is 3, and 17 over 6 is not 3. It's 2.8. So this is the credibility estimate of lambda 6 times 14 over 5. Yeah, okay. So this thing should be used. So this is the posterior distribution for lambda given x. This is the gamma of these values. Okay. Gamma of these values. And we have the credibility estimate lambda, which is 2.83 in this case. So let's just use the proper example. Set the lambda, set the gamma values, and find out what can we do here. So suppose that the annual number of claims resulting from water damage is that lambda equals 160, and we have the gamma distribution 120 with beta 1, and this is underestimates the reality of the situation. Let's say that we were collecting data, and after n years of data have been collecting, this is example 0.6. Where's my mouse? Can't find my mouse. 6. We have 12 years of data collection, and the formula that we are using is n over n plus 1 times x bar x plus fraction of 1 over n plus 1 times 120 over 1. So this is the formula that we are using, and what is the credibility factor in this case? In this case, the credibility factor is just the first value, right? N or n plus 1. So the credibility factor, it always using the linear combination. So as like here, we're using the linear combination zx plus 1 minus z, something like that. So the credibility factor is something which is in the first place always. So the credibility factor z is n over n plus 1. Okay. This thing, what is happening with this credibility factor actually? It converges, and it converges rather quickly to 1. And in this instance, this is crucial since the prior information on lambda gives little credence to values as large as the actual value of 160. However, that had one used a more precise prior for lambda with the same mean, then convergence of the credibility to 1 would be slower. For example, if the prior were not the gamma 121, but gamma with, let's say, gamma, let us place large values like 968, distribution with the same mean 120, then the corresponding credibility factor would be quite different. So these values would be changed, and they would be changed like n plus 8 less than n over n plus 1, right? So in this case, this value less than n plus 8 will be less than. So we'll have this kind of corresponding credibility factor after n years of data. Okay. So this is what is happening if we're talking about gamma values. Okay, it might not be that clear, but still quite useful for our case. Then what can we actually say for here? What would be the priors, and this will be like your maybe homework. What would be the priors? Let's say the claims are the vector of 156, 150, 157, 150, 167, 134. Let's say that. And we have the priors of gamma, initial gamma, and the next gamma, 120, 1, and 960 and 8. So this thing is actually vector of 138, 142, 146, 147, and 150. This is the credibility estimate, and this is the credibility estimate for this value of gamma, 131 and 134. So if we continue that with different values, what would be the estimates of gamma 121 and 968? So this might be the case for you to think at home. Okay. So that might be a lot of questions for here. And actually, we will consider this example next week. We'll check that. And Actually, don't worry if you don't understand right now here anything about these normal and gamma, how to say it, Poisson gamma models. This is all right, but we will place some emphasis on this on these explanations next week. Okay. So I think this is enough for the second part. I would stop the recording and we will meet in 10 minutes, 11:15. If you have any questions, just place in chat. Thank you. Continue.